Buen día, buenos días. Always when you think that you have been or you are interested in many things, maybe it's because you are not very deep in any of them. But I got lucky that at the time of my PhD, I have strong connections with several people here, and in particular during my PhD with Concha González. She was my advisor. I remember in 1998, after the result of Super Kamiokande, where they showed that the number of neutrinos coming from above and from below changed with a pattern that was showing that there was this flavor change between the muon neutrinos and other flavor, in that case tau neutrinos. He said, oh, this is now understood. There is this other problem, solar neutrinos. And then she left to Brazil. So after 3 months, she came back and she saw that with another student, we have our wall full of plots. And she said, oh, well, then maybe we can do something with this guy, and then we started. That was a fascinating time, because in very few years, then all data and ideas just collapsed to really deeply understand what was this solar neutrino problem. It was lots of fun. And then I have interacted with several of you because you know, this is a field, the field of neutrinos, that has all these connections on what is the relevance in cosmology, and also all these weak interacting particles. Then they share this similar type of techniques. But I will discuss about underground labs, and this is a fascinating time just to go and try to help the experiments that are being developed there and the techniques. And in this diagram, you can see different underground labs in the world, depending on how you count them. But typically, if you have on top of your experimental area about 1,000 tons per square meter, then you have about 10 to 12. Some of them are experiments. That means only host one experiment, and several others there are facilities. And then among them, there is this one that is Canfranc, that is in the Pyrenees, and I will discuss about it. The reason why we go underground, or we have to go underground, is going to depend, of course, on your experimental activity, but in particular for the main experiments that are dark matter searches or interactions of neutrinos with matter, then you need to evade all this shower of particles, mainly muons, that are going just to blind your detector when they pass by. Well, if you have a technique that is able to just resolve the time of the passage of the muon and all the light that is producing, you could leave it in the surface. The thing is, you will have to lose lots of time reducing that. But more importantly, even just if you are safe from this light from the muons, then these muons are going to activate nuclei in your detector. And your detector, even if it is very radio pure, is going to become non-radio pure just because of this muon. So you have to be safe underground to keep clean your detector from the radioactive point. That's the reason why it was built, this lab, and this lab is integrated in a kind of a structure of other installations. So you cannot read it very well. Here is said Canfranc Underground Lab. It's placed here. You divide from coast to coast in thirds, and then in this first third from the Basque Country, then you have it here in the frontier between Spain and France. And there are several others. And just to get a name of it, this is a ICTS, this Instalación Científica y Técnica, singular. And then you have several others, in particular in Barcelona, certainly you know ALBA or the Supercomputing Center, etc. And we share the similar type of administration, which makes our life, in many cases, very simple. Of course, you have to suffer administration. But how this started? In fact, this started not by science. It started just because, at that time, the King of Spain, this was 1895, and the president of the French Republic, they met and they said, well, let's build a train connection between Zaragoza and Po. And then they found that the best location was on the Spanish side. They just flattened the area, plant several millions of trees to avoid floods of snow, and then they built this magnificent building in the middle of the mountains. This is called the Canfranc International Train Station, and a train tunnel of 8 kilometers. And then the pioneers in 1986 from the University of Zaragoza, both Morales brothers, Ángel and Julio, and José Ángel Villar, and then also Rafael Núñez Lagos, they started exploring the possibility of using the train tunnel and the facilities in the neighborhood just to use it as an underground lab. At that time, the train was not running anymore because since 1970 there was an accident on the French side, and then the train line was not used. And they started coming in and doing some measurements. This is a This is a representation of the lab of the underground tunnel coming from the Spanish side. The elevation over sea level is about 1,200, and then you go in, and after 2,400 meters, then you have on top of you the maximum amount of rock, that this is 800 meters. So at the end of the 20th century, they built the road tunnel. And at the end of the road tunnel, 2003, then before just bringing back all the equipment for the construction of the tunnel, then the scientists, these professors from University of Zaragoza, they asked the ministry and the authorities just to build an underground lab. It was relatively cheap. It was built, finished in 2006. And then the first director appointed, Sandro Bettini, that he was so lucky that after 2 weeks, part of the roof fell down. And then the lab was delayed in activities for about 3 years. Of course, the lab paid for the reparation because, of course, these companies, they found a way just to escape from. But at the end, it was solved, and in 2010, the underground lab started. So next June, we become 10 years old. So it's reasonably young, and that's why maybe several of you don't know much about what has been going on there, because people there have been working, particularly several experimental groups bringing their activities, their experiments there, just making sure that it works. And as you know, in any experimental activity, you need some time just to make things work. Then after this great job by Sandro Bettini that made the thing work in difficult times, then the second director appointed was Aldo Ianni from Gran Sasso. Then you see that we have strong ties with Gran Sasso. I will mention afterwards, but the Laboratorio Nazionale del Gran Sasso is the largest underground lab in the world. And then from then we got lots of experience, lots of help from the engineers, etc. And that make also that this time is not too long to make the lab working. So those are different measurements, and then the important thing here is compared to what you see on sea level, that is about 1 muon per square meter per second, here you have this reduction of, in fact, a few, so a reduction of a factor 3,000. So this is the layout of how the lab looks now. So you come from the Spanish side, so then you just drive 3 kilometers, then you have here an entrance, a double door just to make sure that the two tunnels are not connected. You come in 100 meters, then you have a parking lot and come in. Then there are several spaces, so let me just name them from you. So this is the service area, so that means this is a corridor and where you have the different services, general services for the lab, electricity, clean room, etc. This is the cosmic silence area. And in there, then I will discuss which type of experiments we have. And then this is the discovery hall, where you have the bigger area, 600 square meters, where we can host ton-scale detectors. There are more labs. Historically, the first ones are this lab 780. By the way, the labs are named just by the distance from the Spanish side. Lab 2400 means that when you finish your day job, then you want to go back to have some nice food outside, then it's just 2,400 meters to get away. I will show you how nice looks the exit when you get out from the tunnel. And, but there were previous labs were this 780. It was some excavated area just to have explosives when the tunnel was built, and also just to make sure that no one was getting into Spain without punishing them. So the thing is that there were some labs there already, very small, as you see, 100 square meters in total. And then when this road tunnel was built, the scientists that were just doing these measurements from University of Zaragoza was disturbing the workers, because most of this rock was getting out through the train tunnel. So that means just For free, they built a lab, so that means they were not in the middle. And then there is this another lab here, 100 square meters. In total, 100 square meters. That makes the second inside underground lab in Europe. And this is a picture of how it looked like a year and a half ago. The main hall, the 600 square meters, where you see in the bottom, this is the next experiment I will mention afterwards, and this is the idea of the size. It tells you that we manage ton scale sizes, and then in here, then this is a lead castle of 60 tons. Inside is another 10 tons. This is a pool just to make sure that if here there is a ton of liquid argon, if it is spilled out, then it's not going outside. This is part also of the experimental area, and those are the two main buildings outside. This is the offices and other services and other external labs in the main village there in Canfranc. And then in fact, this is the first building in the area built for the engineers that come just to design all this structure of the area, and now has been refurnished and restored just for the lab, just to host meetings and exhibition room. For the ones that have been there, just let me tell you that now the lab doesn't look like it looks 1 year and a half ago, because now it's busier. So now all this swimming pool area, this pool area, now is filled with a clean area just to host the expansion of the experiments, in particular the expansion of NEXT. So I will just divide in two pieces. Is that, first of all, what is this lab? It's a facility for you. So you have an idea or an experiment or a design that you want to test, avoiding these muons and all the radioactivity and all the perturbation you can have. Come here, and the lab will provide several services. So I will not go through all of them, but just sketch some of the main components. One of them is that, first of all, whatever comes into the underground lab, then you have to characterize radioactivity, how radioactive it is, which components there are there, particularly potassium-40 and all the uranium and thorium, all the uranium and thorium chain. And for that, we have germanium crystals. Those is typically 2 kilograms. Those are semiconductors that are nitrogen temperature. Then you can just proportionally read the energy of the photon, of the gamma ray, just by the electricity, by the amount of current generated. So at the end, this is that's gamma spectroscopy. And with these lines, you can identify by how much your component is radioactive. There are 7 running all year. When radioactivity is very low, typically millibecquerel per kilogram, so that means 1 disintegration every 1,000 seconds per kilogram of material. That means that typically you have to stay, your sample has to stay there to be measured for 1 month to 3 months. And that's why this room is our 3-star Michelin room. So that means you have to wait months just to get a table there. Other services, and I will discuss just very little, but are the standard that you may need. This is a room just to open your detector and make sure that doesn't get contaminated. And one of our main services is also that we provide radon-free air. One of the things that we learn is that it's not only you have to be clean, also your environment has to be clean. We renovate the air 3 times an hour, 10,000 cubic meters, but the radon in the standard environment that is sufficiently good for humans is not for experiments. So you have to significantly reduce the radon in the air. First utility or help that the lab can provide to experiment is shielding. Even that you have the rock, this 800 meters of rock, the rock in the neighborhood of the lab is producing gamma rays, neutrons, is just producing lots of radioactivity to your sensors, so you have to protect your sensors. When you go there, it's a very nice visit, but typically you don't see the details of the detector because it's protected from you, that you are very radioactive for the detectors. So how you protect them, depending of course on the source. If you want to protect from neutrons, the best is the closest and most popular particle that has similar size. So that means you take something that has lots of protons. In this particular is polyethylene. And then depending on the thickness, then you reduce more or less the neutrons from outside. Then if you want to protect from gamma rays, then you put the highest density material you can. Gold will be great, but very expensive, so we use lead. And then we have lots of LEDs in there, more than 100 tons of lead that can be used for different experiments. And if the lead is not the one that has been protected underground, the Romans were just telling us, we will save lead underground sufficiently time, 2,000 years, just to make sure that this lead is not activated by cosmic muons. If you don't have this ancient lead, then what you do is you take the best lead you can find, and you protect internally by this kind of shield of box of ultra pure copper. And this is the type of facility I was telling you. This is one detector, particularly this is next 10. This is the lead castle, but in between there is air. This air is producing half of the radioactivity of this experiment. You have to remove it. There are two ways of doing it. You remove with nitrogen. You pay lots of nitrogen gas, and then you just pure nitrogen there, or you use air where you have removed the radon. Some pictures. 2019 has been very good for us for just making investment in improvements. One of them is our gamma ray detectors are among the best in the world. There are 2 or 3 places that have somewhat the top level. There's only one crystal that is the highest is built in Germany 20 years ago and is hosted in Gran Sasso. And then this is kind of in this second step and comparable with all the other germaniums in the world in 3 main places. The thing is that we want to do them better. And then we got some funds just to make sure that we replace components and make them cleaner. Other type of project is you may need components. Sometimes these components are copper, and then you go to the shop, and then you get the best copper. Still, this is too radioactive, so one way to improve it is just dissolve it and reform it again. This is called electroformation. And unfortunately, then you will have to machine it, and then this will clean it. This will just add some dirtiness. So one of the ways that is now being tested in a collaboration with Gran Sasso and Canfranc is just produce the best copper you can, make it powder, and don't touch it. Just place it there, and with laser, then you just 3D print the element, the component you can. That will make that your components are the lightest possible. Because there is a kind of common rule, is if you want less radioactivity, put less material. The other 2 things that are going to happen in 2020 is we will have an instrument that is derived from an experimental activity that is called DAMIC, that started in Chicago and is moving to the French underground lab, and is having a tool to characterize CCD, particularly wafers. So that means if you have a CCD, silicon CCD, and you want to characterize how much activated has been this silicon by cosmic rays, then we will have a tool that may be important. In fact, is becoming very important for several types of detectors. And then this particular one, I will discuss it, and it's a fantastic example on how the Canfranc lab may help your idea. So let me just discuss it. This is an example. This is our facility. Those are collaborations with experimental groups. So that means this impact is from Krakow in Poland. So they build this for us. So that means we pay the components, and they do R&D at the same time that they produce them. But let me go. This is copper electroformation. This is the best copper in the world. It's below PPT, 1 part per trillion. And if you just dissolve an electrofold, you reduce typically about an order of magnitude or even a little bit better. Let me just illustrate, just as a service, what you can be useful for the lab, and maybe the lab can be useful for you. A few years, one of the problems in some of the experimental physics, in particular, I will mention in double beta decay, is that one nucleus, in this case xenon 136, just becomes by double beta decay in barium 136. And that produces electrons, and this is what typically in particle physics we have expertise on, measure properties of these electrons, energy and the tracks. So, but because in this process also you produce barium, you could try to distinguish one atom of barium from this bunch of lots of xenon. This is what is named barium tagging, and then this has been an idea around for more than 20 years. But then Dave Nygren just reading in other fields, sneaking in other fields, they just came to his hands the work by the Nobel laureate in chemistry 2014, that was just how to use capture of calcium in neurons with this technique, super resolved fluorescence microscopy. He got this idea, and in the US he implemented in a realistic case for capturing barium, and he demonstrated that this works in solution. First step. David Nygren is, I will mention afterwards, is one of the co-inventors of the next experiment in Canfranc. So the group said, oh, this is interesting, but this is not what exactly we need, because they have a ball of gas under pressure, so not a liquid. So they have been just working in the Basque Country, just how to change from some fluorophore in solution to something in gas, dry. And they came this year to some molecule, they build it, they use this quantum chemistry calculations, and then design a new molecule. They call it FBI. And then the molecule basically has some, as many of these organic molecules, all these, they are called pi states. Basically, it's delocalized electrons, which help a lot in where you absorb light. And then this is what is a corona structure. And what it does, so if you plant it in a solid surface, then the corona stays there like this, and when a barium cation passes by, grabs it and bends. And the impressive thing that they designed for, and then it works, is that the amount of light that when you illuminate with a laser that fluoresces from this molecule without the cation and with this molecule with the cation is more than a factor 10,000. Still, they don't know how much more is below, because they cannot even measure it. So they are building an instrument to measure how much different is the light. This is very important, because if you have many molecules that don't have a cation and you have only one, you have to make sure that the noise from all the other, you are exceeding it with one. Well, I went to this meeting that they have, because this is experimental collaboration that works for Canfranc, and then I have just a very minor contribution. I told them, I buy the equipment that you need to demonstrate your technique, if you build it not to capture and demonstrate for one atom, but only for a few thousands. Let's simplify the problem a little bit, right? Instead of barium, I wanted radium. They said yes, and then this was late May, early June this year, and in October we have the budget approved. And the experiment starts building now, so all the installation in January this year. Why we can do that? Because this is going to be a new type of technique that can reach 10 to the minus 18 parts per part. This is below anything that has been done analytically so far on capturing radium. That is one of the isotopes that is very radioactive and contributes for the radioactive noise in samples. So the thing is, we can help experiments just to go faster in some of these development of techniques that are useful for demonstrators of their experiment. And the advantage that gets the lab is that we will have an installation in a year or two. Then we will have an installation that in principle can be a novel analytic technique for what we are experts on in low radioactivity techniques. So if you have some similar idea, please come, and I will be very happy just to discuss. This, by the way, is just already on the archive, and it's a paper that is under referring in Nature, and it's really a fantastic step forward. So let me just move to activities that really are the focus of the experiment, not only just provide services, but also host experiments, which is the main goal. So there are a list of them, and this list has been, some of the people in the audience have been in the scientific committee for many years. So, but I will just mention now that 4 of them, NEXT, CROSS, ANAIS, and RDM, they make significant progress along these several years, and now they have very beautiful results. Some other activities are contributions to experiments in other places. This super K gadolinium, for the ones that don't know it, is in the big super K detector, 45,000 tons of, so it's 45 kilotons, right? 45,000 tons of water. Now they are going to be doped a little bit, added a little bit of gadolinium salt, to make the system more effective capturing neutrons. Therefore, they will be good also not for seeing neutrinos, but distinguishing from antineutrinos. And then this is happening now. But this gadolinium salt has components that are very radioactive. So it was an extensive work of 5 years just to figure it out how to clean it up from other radioactive components, this gadolinium salt, and most or a significant part of this work has been done in Canfranc in collaboration with the Super K. Some other activities are not directly neutrinos and dark matter, but are other experiments that require being underground. I don't know if you have been with this formation of a collaboration of Einstein telescope, but the idea is that on this wave of very often now the events detected in gravitational waves, one of the futures is, of course, going to space to avoid all the noise that is produced on the Earth, and the other is going underground. One of the particular noises that you cannot resolve is that when let's say, terrestrial wave passes by, is displacing a little bit the atoms, and then it creates a gravitational field locally. That's why it's called Newtonian noise, that you cannot avoid. It's going to be there either way, even if you just, with lots of systems of suspension, avoid that. So this is unavoidable on Earth. The only thing is if you go underground, it's more stable, and you can suppress it easily. So that means this Einstein telescope is based on going underground. So some places have been observed, and one of them is Canfranc, and now they are down selecting. Most probably will be not the best place, but the one where you get the budget, because this is a significantly expensive project. And the other activities I will mention very briefly is biology. So imagine that you are interested in going to an underground lab. It may not be Canfranc. So there are several, I told you about 12. It's going to depend, of course, on your requirements. And the requirements will be, and then you will have to think about them, is access and space, which support you need, which utilities you need, which services you need. But also you have to worry about protocols. So in an underground lab that you have to go 2 kilograms down, it's very different just to going with your car inside. So that means different underground labs, they have different characteristics, and also, but they have some, they are very useful for many reasons. One of them is, in many cases, national labs are really hubs for the experimental groups. So that means you can develop your prototypes and then going to a bigger, etc. And then there are several aspects that are very important, that are location and depth. That means will limit your backgrounds, and also important how accessible it is. Of the ones that are in Europe, the biggest one I just mentioned is Gran Sasso, started in '87. Even there were activities in Canfranc before, as it in the current stage is 2010, as I mentioned. And then you see Gran Sasso is the biggest by far compared to the others in Europe, also in size. And one of the elements is you have to worry about how limited has to be your muon flux, because depending on how limited, for example, for dark matter detectors, and the cross sections that now you have to be sensitive to, you have to be really very deep underground. And then Canfranc maybe is not the right location. So let me tell you a little bit, very shortly, about some results from few experiments in Canfranc, the most relevant in 2019. Anais, very briefly, you see this lead cover. Inside this is this structure of copper. This structure of copper is electrophore copper built in Canfranc. And inside you will see then they have sodium iodine doped. It's a monocrystal of 12.5 kilograms. That was the most painful part of the experiment, because it took years just to get to crystals that were reasonably clean. Because if not, just the dirtiness in radioactive. So dirtiness is very little, but it's still sufficiently large for the sensitivity that you need to dark matter. That makes them several years just to make sure it. Each crystal takes about 4 months just to be built once you understand how to do it. The other experiment is next, and I will talk explicitly about it, but this is a nice picture on one of the sides. This is all the cabling that is getting out from the silicon PMs, and this is the structure, and as you see, it's basically a cylinder inside with gas. This is one of the pictures of one of the planes of PNTs from RDM, the detector of 1 ton of liquid argon, and this is our new toy that this is the part in a cryostat that works at 8 millikelvin. And this is the design of the cover inlet that in fact was built and paid and designed by the lab. So that means that when you come and you have some idea, the part of the shielding, then let the lab help and support you. Well, just to mention very briefly, I will start with double beta decay. I know that here you are, of course, there are lots of experts that let me just very briefly say my way of seeing what is the motivation for these experiments. Of course, if we just consider what is basic in the construction of the standard model, then you have on one hand these gauge symmetries, then in the construction of components is chiral states, and then spontaneous symmetry breaking. And then within, then you have basically your family of, your first family that defines mostly what we have, and then all the other components in the second and third family that, as you know, we don't know why it comes in 3. But all these states are organized, as you know, with 4 components that are both chiralities, if you go to mass states helicities, and then both states of charge, the particle and antiparticle. And these are the 4 Dirac states associated to each of these squares. And the special characteristic that has in this diagram neutrinos is that in the plotting, diagrammatically here, we are saying that are fermions like the other ones. But one of the possibilities when one looks at the construction of all the interactions is that instead of looking what I have to add to explain things that I don't understand, dark matter of others, is what is left. Based on these symmetries, on these basic rules, and knowing the components in nature that I have observed, when I write all this, is everything that is permitted by these basic rules. And then it's very well known that there are 2 components that might be there, and so far they are not. And one of them, and then this is what in other words is called that all these terms, it was not demanded in the basic structure, but then preserve lepton violation. But there is one term that in fact incidentally was invented by these men, Majorana, that in 1937 his friend Fermi submitted a note trying to address the issue is whether you could just have an alternative to Dirac states where you don't have this problem of negative energy, this problem of particle, antiparticle after was understood. And then yes, he found that it's possible, only of course for neutral states, and then we have an alternative that this is, instead of having Dirac states here, then you have Majorana states for the light and for the heavy. So that means you split these 2 states in, and in the interpretation before, for those that don't work on this here, where you have the 2 chiral states and the 2 particle-antiparticle states, here particle-antiparticle is understood like one chirality and the other instead of the state with the same mass. So we don't know which one of the 2 pictures is correct. And then there are some arguments, some hints that may tell you that maybe this is the right picture. Still, we don't know. Maybe the Higgs sector is so strange and complicated that we live in that sector and then they are so different just because the Higgs and all the lack of knowledge that we know about how it works. So the hints are the following, and then you have a worldwide expert on this that is telling us regularly that with more and more precision, the neutrinos in this mixing between the 3 families, they behave very differently to the quark sector, which could be just be done by the Higgs, but then the Higgs has to know that leptons and quarks then behave very differently. This could be possible. The other thing is that if you look at the masses of the neutrinos, then they are significantly lower, even that the spread in masses is so large that means that we don't understand very much about how flavor behaves, then it is true that neutrinos are especially separated from the other bunch of particles. These 2 hints somewhat point that this is a possibility, that then there is this split in 2 different types of particles, then the famous line neutrinos that we identify like neutrino, antineutrino, but will be the same state with the 2 chiralities, and then these other singlets, and this will be very easily incorporated in a term that is the one that is not changing our general scheme. we keep the same idea of gate symmetry, chirality, and spontaneous symmetry breaking, because this term is not perturbing that. But if that is the case, then new phenomena happen. And of course, one of the interesting phenomena, and then I'm just concluding this very, very quick summary, is that this process may happen. One process where from somewhat the quartz sector, you are generating total lepton number. So that means all this story, the conclusion that is telling us is that there is a process, a new process that is able to violate lepton number. And then through processes, non-linear processes in the standard model, then this may be even converted to barium number. But I will just concentrate on this because then this is a process that is interesting. The process is called double beta. When it produces electrons and neutrinos, it's a standard model process. It's true that it's second order. It's difficult to measure, but has been observed for several nuclei. Which nuclei? Those ones that they don't have beta process allowed. If the energy of the beta brother is higher, then you cannot go beta, so you stay longer, but you may find a double beta sister and then go there. And the thing is that the half-lives are very, very long. Typically, the bound nowadays is 10 to the 26 years, and it could range from 10 to the 26 to 10 to the 30, let's see, unless there is a magic cancellation that even go to larger half-lives. So very difficult to measure. Just to give you an idea, if you have 1 ton detector, and you take 10 to the 27 years, that means that you will have 1 decay per year in all your full volume. And that means that you have to be clean to remove everything. So that means you should have something like better than 1 event per year of noise, of radioactive events, just to distinguish this event per year. So it's a very challenging problem. And moreover, then this half-life is what you measure, and then you will observe, etc. And making a connection to fundamental physics is through this expression where the masses and these mixings is what is obtained in the plots that I showed before, where you get all these mixings. There are some phases that are unknown, but you can determine some kind of parameter that connects the half-life with this fundamental part of neutrinos, but through nuclear physics, through this process that is producing this double beta decays. This is the nuclear matrix elements, and very shortly I will mention just some problems with it. So this is a clearly very important and hot topic, and there are groups working on it for many years. And particularly in Europe, they have gathered together to, at the end, get some report where they down select to 3 strategies. And among these 3 strategies, we are very glad that there are Legend, which is using the germanium detectors, but the component, the isotope that is double beta decay, that is germanium 76. So you enrich germanium, you take it only the double beta decay isotope, and you use the germanium technology to keep measuring. Is the technology that is leading the field nowadays. The other is this Cupid, that is an extension of a detector that is quarry, that is using cryogenics, using crystals that behave as a bolometers. You can measure the variation of temperature given by a particle passing. You can identify the type of particle. They have found lots of noise on the surface, so they are trying to solve it just modifying it. And modifying the surface, one of the techniques was using aluminum foils, and then there is a connection with the people that do quantum technologies, because at the end they become superconductive and they are learning technology that may be used in that direction. And this is the other technology. And the third one is the one I'm going to discuss. We have some contribution here, I will mention. And then the other one is next, which is the experiment that we host in Canfranc. So these 3 experiments, 2 technologies are, one technology is fully done in Canfranc. The other technology is R&D is done in Canfranc in France and in Italy, and the other technology is in Italy. So that means we really are in good position in this business. So this is what happened in 2019. Again, cross, build, and then this is taking data on molybdenum crystals, molybdenum 100, and they are working on that. So let me go to next, because I will spend a little bit of time here. What next is trying is just, it has a bunch of xenon 136 atoms in gas phase at pressure, and is waiting for this to happen. So that means that spontaneously, in the middle of this, well, in some part of the detector, in the gas, then appears a barium, and at the same time 2 electrons with total energy of the difference of mass between barium and xenon. That's the goal. And understanding that may happen once per year if the half-life is 10 to the 27 in 1 ton. The idea that was invented by David Nygren and Juanjo Gómez Cadenas was the following. Well, xenon is fantastic because being a gas, whenever an electron is generated, the electron is going to scatter different xenon atoms, and in this scatter is going to produce light that you can collect on one side, and it's going to produce electrons, and if you add an electric field, then these electrons will just migrate, you amplify, you become it light, and then you measure it. This is a PNT plane that they added, and then this is a silicon PM plane. And the idea is they can measure at the same time the light producing in the event, that means the total energy producing in the event collected, and also see the electrons, tracking them. Because there is lots of noise and you have to reduce it, the idea of this novel technique is, with novel gas, is not measuring only the energy very well, because remember, in this process, the fantastic thing about this is the 2 electrons get all the energy from the nuclear process. So it's going to be a line at the end point of the double beta spectrum. So if you have very good energy resolution, you will measure exactly this peak. It's going to be very small, but in principle it's a good line there. But many other things may become similarly and producing lines nearby your energy event. So having other processes that can resolve it, or ways to know it, that will be important. And then those are references that you can go, 1905, where they show, first of all, the detector, which is here, and was a prototype for 10 kilograms. So it means they cannot observe double beta decay. With 10 kilograms, you can reach 10 to the 25 years. And informally, they are reaching that number. So, so this is the bound that they are about to publish. They will take a few more months data because we are in the phase of building this factor 10 bigger. And then the other thing is, this is they measure this energy better than, or at the level that they were anticipating, better 1%, so they can resolve this line. And the other thing, they can see the electrons. And this is just figures, real data demonstrating the effect. Because for several years, when you have a design and you build them, then you have simulations that tell you what you expect. So here what you see is a real event. So at some point in time, you see the light from the electron produced. And then after some time, this electron has been traveling, creating other electrons by excitation of the xenons in the gas. These electrons are tracked with the electron field, and then you see them arriving at different times. And from there, you can reconstruct where the electron is coming from. And then you see here tracks of 1 electron, this is background noise, and tracks of 2 electrons. This is double beta events. The energy of these events is not the energy in the peak. So these are not double beta, neutrino double beta events. Those are events of this double beta spectrum, the standard model one that you expect. And the energy resolution at the right energy, you're looking something that is around this energy, 24, is very good and better than 1% as they anticipated. So the success is the technology works. Okay, when you have a technology that works, then you ask for more money and you make it bigger. And then we have the money, well, the experiment has the money and the laboratory is supporting them just to go from this 10 kilograms to 100 kilograms. That will mean if you keep background at the same level lower, means so your half-life will increase or your sensitivity to 1 order of magnitude. And this is the goal for this year. 2020 is very busy just to make this thing working. And then what was discussed at the international level is that this is one of the technologies that can go to the ton and then get to the 10 to the 27. Okay, so this is a big competition. And then you see here the different techniques competing. And as I said, for us, for the lab, it's really very relevant that we are in the competition. which, as you know, in science not always is easy. Just really being at the forefront and try to fight to be the one that can reach better first this half-life where the event is observed, we hope. Well, how you convert this half-life in something that is these fundamental parameters? This is one way, there are several, but the idea is that because you know the expected signal from the neutrino masses, and if you believe the calculations that people like Javier and others do, then you can reconstruct where do you expect the signal, and this is the region, this is the sensitivity that we have today in this parameter that is just the neutrino masses, and this is the region of expected. You can see here that there is in principle a potential go to escape. It's very difficult to go very much lower, but potentially you will not cover in the next generation all the region, but you will really make touch a significant fraction. If you have questions, I can discuss it more about this. But there is a problem that is hidden, and this is the problem that in the community, well, most of the money in this, of course, goes into the experiments because you want to observe it, but it has been recognized by the community that this is very important, the nuclear matrix elements calculations. And this is being done now in the US with some support, and some national labs are really making an investment, particularly in Oak Ridge, the groups there, but also in Europe I think has been recognized, and I hope that this will be very good for supporting a lot one of our, well, you are very lucky because you have one of the global experts in this. And then with a student that is living in Canfranc, that is Beatriz, that is around. And Javier, what they are trying to do is the following. Because if you spend a lot of money on this, and then the nuclear matrix elements are wrong by a factor of 10, what are you testing? Right? If I knew that this estimation from theory, what is observed is half-lives, but from half-lives to a kind of combination of fundamental parameters, you have to introduce these nuclear physics calculations. So if you don't understand them within an order of magnitude, whatever I spend 100 million, well, several tens of millions, let's say, from going to here and there, then it will be really not very useful, because then the calculations are telling me that you were mistaken. This was much higher, and now really you are in this place. Well, that's why some nuclear theorists are bringing new ideas. And one of the ideas that I find very interesting is the following, is, well, it is true, nobody measured neutrinos double beta decay, so how can we do anything of theory and make sure that we do it right? Well, one of the ways is just trying to compare with processes that resemble somewhat, and then that try at least to include similar type the components in the calculation. Nobody can do these calculations at the ad hoc level, so that means with our approximations. But what you can do is compare to other processes that are double Gamma Teller, and then in this case, the comparison is with 2 photon processes. And if you go to 2 photon processes, there are some correlations that are found at the theoretical level for some numerical type of methods and not for others. And this is a test that experimentally you could in principle. Well, theoretically you can verify, and experimentally as well. And then if these 2 photon processes are measured for neutrinos double beta decay nuclei. Well, let's see what the output of this is, but it's very interesting. Let me just go quick, because we are not a lab that can do very big dark matter detectors, and the reason is because you will be filled with lots of muons and the radioactivity induced. So now big dark matter detectors have to go underground, and much more underground than the typical underground labs like Canfranc or even Gran Sasso. The next labs that will be just hosting the biggest detectors in dark matter will be Snow Lab, that are very deep, and very soon will be another actor that will be China, that is going to host the largest underground detector, just by a little, with respect to Italy, and the deepest. But Canfranc is doing some contribution that is interesting. As you know, the motivation of dark matter is we don't know what are the other components in the energy budget on top of the very small that we know that is us and all the physics that we have learned. One of the possibilities is that this is a particle with mass similar to our nuclei. And if that's the case, then it's kind of optimal to measure how much energy is transferred, and you can measure heat, charge of light. And then there has been lots of searches and nothing found. And those are the bounds. In cross sections that if you come here, if there are nuclear physicists here, you are going to smile, because this is 10 to the minus 48 square 10 centimeters, 10 to minus 24 barns. So this is really very small cross sections. You know, the detectors are so big, ton scale, and they don't find events, and they are so clean that really you can go very low. Nothing has been observed, except once. There is one detector in Italy that, with lots of noise, but exploring how the signal changes with time, if there is a dark matter wind, and because we move around the sun, then you will have sometimes this velocity effect that increase or decrease just because in the cross section with a target you have this dependence on the velocity. And this is what they observe. It could be many things that change seasonally. One of the possibilities is that dark matter, but because no other experiments has found it in the region that this should happen about here, in 10 to minus 40 or so. So how to solve this puzzle? So many years ago, 15 years ago or so, there was an agreement that someone has to repeat the experiment in the same conditions. This is what Anais is doing in Canfranc, and also Cosine is doing in Korea, and also the Americans of Princeton are trying to repeat in Gran Sasso. For the moment, the one that is leading this search is Anais. Even being so hard, they were able to build the largest, best crystals working nowadays, apart from the ones from Dama Libra. And the main result is that so far they have 2 years of data. And this was presented in 2019 for the first time. No modulation is found at 2 sigma. This is so if you compare, this is the result by Dama Libra, by this Italian experiment. So they find modulation with many sigmas. I'm not saying that they found dark matter. I said they found modulation with many sigmas. And this is what Anais finds so far. Of course, statistically, they still are not so good. They need more time. And the idea is that within 3 more years, they will go through to 3 sigma. And after that, maybe radioactivity will prevent to go better. But at least there will be some, with the same technology, with the same type of detector, try to see whether there is modulation or not. This is in the same data span, how it looks one or the other with the same data. So it's not seeing in the Anais data any modulation so far. Also, other experiment, which in fact is not an experiment, is a tool, is that if you use argon as a detector, it's very nice for dark matter compared to xenon because it's light. So it means you can go to light beams, but it has a problem that argon is activated with muons. So there is lots of radioactive argon, argon-39, then that it will prevent you to go to low energies. So one of the tools that is going to be built in Canfranc to help this global argon dark matter collaboration is to install inside the detector, inside here, some small capsule with a little of this argon and measure it. And the rest of the argon is going to be just shielding your equipment. And this tank is just to make the argon at 192 degrees below zero, moving from one place to the other whenever you want to access it. Okay, so let me just finish this part, and then I'm close to conclude, that several other applications are for 2020. So in the experiments are the dunes, in crystals of sodium iodine, in barium tagging, in liquido, that is a liquid scintillator dense for double beta decay, or in a biological lab. I'll just conclude with some entertainment for you. I guess that there are not many biologists here, so you will understand very well how simple things come to my mind. That is, I was just walking in the train tunnel with the director at that time, Sandro Bettini. He was making fun of me because I was analyzing some microbiota from our gut, from some samples from some PhD students. I was just trying to understand something. And then Sandro Bettini was making the joke that Carlos is changing neutrinos por mierda. He loved this Spanish word. So, well, in any case, he did something interesting, is that, do you have any idea that what could do in biology in the underground lab? And I came with this basic idea saying, why don't we drill in the mountain, get very cheaply some cores, and try to see if there is anything there. I thought that it was crazy by myself. I thought that it was interesting and very cheap. Microbiologists will tell us that, of course, you are going to find life there. Now I understand that, but I didn't at the time. In any case, we just make something very simple, characterize this, take powder from the internal part, sample it, measure it, and then, of course, make the hard part. And the hard part was 3 years of a PhD student doing all this pipeline of codes to really strongly and deeply analyze this data. Because the thing when you don't know what you have there, you have a mixture of living bacteria and archaea, and then the information you are going to get is of all of them mixed. It's like having millions of puzzles, and you only have a few pieces of several of them. And you have to reconstruct how many and different types of puzzles you have, right? Yeah, this was a brave work, and the postdoc now, the student now is in Berkeley as a postdoc, so he did well. But the conclusion that we got was very simple, but very relevant, and sometimes even for a project that was 10,000 euros. Is, first of all, we sampled different places in the tunnel, but in one of them in particular, we found that there are lots of archaea. Archaea are our cousins, are in principle, we are eukarya, as you know, our cells, and our cells are very far from bacteria, but there is this kind of bridge that is called archaea, where we share proteins in the membrane, etc. It seems that archaea at some point were our bridge, but then bacteria almost killed them. Maybe this is telling us that be careful, because they maybe afterwards kill the eukarya, I don't know. In any case, we found lots of archaea. It's very rare, because whenever there are bacteria, they kill archaea. And they share the same type of species that when you go to the bottom of the sea, you found there. But this was natural, because the Pyrenees at the end, 20 million years ago or so, were the bottom of a sea. And very interestingly, these species that are also found there, we identify molybdenum, very large amount of molybdenum in the samples with this bacteria, with this archaea, sorry. This was, by the way, the first time found for this type of samples. And the experts on this, they came and say, oh, this is very interesting, because in fact this is connected with a big project that we are doing in the US to Chile. They are just sampling some in this branch where you have lots of material coming from the inside of the Earth, because they want to explore the hypothesis that why there were lots of proteins based on molybdenum. You know that many of our proteins really, they have a metal inside that is used as an acceptor of electrons, etc., make the proteins work electrochemically. And then it seems that about 2.5 billion years ago, most proteins took molybdenum, whereas you know now some of our more important proteins, they take iron and other metals. And this is still not well understood, and then this is a hint that they may go in the right direction. It's far from my expertise. But this opened up a connection to several people that they are trying in different labs the following. You know very well that here outside, on ground, if we receive radiation, our life gets damaged. So there is this issue that more radiation gets bad. And that was the first approximation that a physicist will do, that will be the linear theory, is that if you go to lower radiation, life will get better. Well, this has been demonstrated that is completely wrong. If you go to more radiation, then your cells may die. The system tries to repair the damages in the DNA. If you go low, the first thing is you stress the cells. Someone, when I mentioned this the first time, was asking me, have you tested the workers there, whether they get stressed or not? Not yet, but it's not such a bad idea whether the cells get stressed. But then there are significant effects of low radiation. But more importantly, what has been observed not only on cells, but also on living systems, on flies. Now there are potential experiments on rats, but physicists said Ingram Sasso said, no, we don't want rats in the real rats in the lab. So, but what it was found, and this is repeated experiments, lifespan grows, fertility gets reduced, and most importantly, the DNA reparation system fails, stops. It's not that you have more damages in your DNA. When you go underground, your DNA reparation system, for some reason, stops, and this is connected with radioactivity, clearly. So that means, as you know, these particles are MEVs or above. When they cross cells, that is a water medium, are going to make a shower there and give energy to the system. And probably, and this is a hypothesis, what it's doing is just activating in this network of reactions channels just to make this thing work. And life has been adapted to be with this radioactivity. If you just reduce it, life has to be refined a new way. So, and that is why this sharing of being in these fields is that it has been approved, and there are several groups that will just join, is just have underground lab on surface and on underground in biology. For what reason? Is for physicists and biologists work together, because one of the important things is it has been demonstrated that dose is not important. It's important the spectrum of particles. So that means whenever you have a biology problem, so far it was biologists and physicists were looking to other side. Is that it has to be correctly characterized what is the spectrum of particles that they are receiving to understand which is affecting more or less. In any case, let me just conclude. Underground labs exist because they were needed, and this is because this progress in astroparticle physics. So, as I said, this is a necessary condition, and neutrinos is a success story. Really, they make them grow, get bigger. Still, there is a hope that dark matter can be found, and then one possibility is these WIMPs, but maybe there are other ideas, and then, as you know, you are contributing to exploring the possibility that this is light particles, name axions. Then experiments have to grow, because the cross sections and the half-lives that you have to search for are more demanding, but whenever you grow in mass, you have more radioactivity, so you have to reduce radioactivity. So the challenges to low radioactivity techniques are higher and higher, and this can be done in underground labs. They are more tuned to that. So, but then let me summarize how I feel, because I was very lucky. So it means many people before me, not only the directors and also the group working there in Canfranc, but many people that make this thing possible, then they have been, that this installation now becomes 10 years old. But, and then I just came at the right time when they did this nice work, and then I can tell you that 2019 has been wonderful in the sense of demonstrating the technologies we have in Canfranc, and demonstrating that the lab can attract, deliver, and innovate. And this is the goal of this lab. But this is done by the groups of scientists that go there, and engineers, etc., that go there and develop their work. This is more than 400 people. Fortunately, they don't come all at the same time. But we reached peaks of 40, so it means there's a significant amount. And the point is, and this is, of course, due to history, but it's a not news, is that there are very few people from Catalonia contributing to this type of physics or science in Canfranc. So I hope that you share this excitement and make use of and be part of with your proposals and ideas to the Canfranc success. And if so, then you will have this nice entrance to the Spanish side. And make sure if you come at this right time, because now this was a picture in January last year, but it's close to this nowadays. So this is the exit when you get from the tunnel, 2,400 meters, you get out, and not every day you see things like this, but it's beautiful. Thank you.
Thank you for this very interesting talk. And now there is time for a few questions if anybody wants to ask. So they're in the back.
So thank you for the very nice overview and talk. In one of your first slides, I was curious because you put the map of the underground lab, and there was an arrow there saying CERN is in this direction.
Yeah.
So do you have any planned experiment that will take advantage of some beam at CERN or whatever?
The answer is no nowadays. But when this was designed, at that time there was the possibility just to build a neutrino beam that could go to any underground lab, And then it was a smart point, you could just rotate in any direction, just have it pointing to CERN. That is the main facility where in the future you could have a neutrino beam. So there is no plan nowadays, but it was built because at that time it could have been possible, and also on the potentiality that this may happen. But there is no experiment nowadays planning to shoot a neutrino beam to an underground lab in Europe.
Thank you.
Any other question? So I have one myself. If the next experiment discovers the double bit of decay, that's fantastic. But if you don't see it, how far can it push the lifetime of Xenon?
Yeah, there is a number, a magic number, that is what the experiments tell you, and I think this is realistic, is that from the current bound 10 to the 26 years, they can reach to the some number in between 10 to the 27 and 10 to the 28 years. This looks achievable. Time scale is 10 years, let's say a little bit plus maybe. If you want to go from 10 to the 28 to whatever, so that means then there is a number said several times that is 10 to the 30, where you cover, basically goes by ranges of this effective mass, that is milli-electron volt. There is a special region, I can explain it very quickly, very easily here. Sorry, here. Here. There is a potential cancellation here that happens when this phase and this phase makes that this sum goes to 0. Okay, that may happen. So that in principle, potentially, so you have the nature has the freedom just to go much larger in half-life and much smaller in this parameter to 0. But the phase space for that to happen is becoming narrower and narrower. So that means it should be some good reason why these phases and these masses and these angles just go and cancel, which are parameters that in principle are not particularly fundamental, are kind of derived phenomena. There is one case that is if the right-handed neutrinos are all very light, I think it's below 100 electron volts, then you may have this type of magic cancellation. So that means there are particular scenarios where this can happen, but are kind of very rare. So that means even that we are in kind of the rarest type of events, then this will be kind of double rarer. But yeah, you cannot escape from that. There are kind of loopholes just for this to escape. Well, yeah, of course, if they are Majorana, yeah, you're right, Concha. So this is assuming that this particular fantastic scenario where the neutrinos not only get the mass from the Higgs, so they have this other mechanism to get the mass. If they are Higgs is very complex, but doesn't violate the Dayton number, and then you don't have this phenomenon. So you can, of course, you don't have this phenomenon. Yeah.
So Cristiano.
So you were saying offline that
Yes.
the Canfranc is also maybe important for quantum computing. Can you expand a little bit this?
Well, there is a group. They were here, and I met some of the. Okay. Hello, Paul. So I met Paul in IFI yesterday evening, and also there is a group here that works more in the theory part of it. That the issue is the following. So they have a small piece, micron size, if I understand correctly, these qubits. This is so very little mass that probably radioactivity there is very little, and the heat of muons there is very little. But they have to cool it, typically to 10 millikelvin, and then for that they place it on a silicon plate, and then this is in aluminum vessel, let's say, or structure. And this is where you have several mass. And the thing that happens is that if muons of radioactivity just produce some particles there, they are going to produce some phonons. In fact, this is the basic technique that Quarry and these detectors use. They use volumetrically, they try to measure how phonons are generated by particles. So they are going to generate these phonons. These phonons are going just to, because there is a thermal link, they are going to travel also through the qubit, and potentially they may just create this they are called quasi-particles, break the Cooper pairs and create some instability and break the qubit state. Whether this is true or not has still to be demonstrated, but there are some indications done, we were discussing it yesterday, with systems similar, also in superconductive states, where they are trying to, they seem to see that, yeah, that radioactivity is very relevant. Doing experiments on ground and underground with lead castles and not, and then they see that there is a significant influence. How significant, etc., has to be quantified, and one of the ideas is that maybe at the end they have to bring some of these quantum technologies, at least protect them, make sure how radioactive are the components, so that means try to screen and make sure that you get the best, and depending on whether this is an important requirement, then go testing underground or even have to stay underground. That is something that should be understood. Is reasonable my answer, Paul? Thank you. So for the moment, they are planning, at least the groups in Europe, they try and they want to understand better whether this is a significant influence or not.
Question? If not, Carlos will be here the rest of the afternoon, and then I want to remind the students and postdocs that there will be today a meeting with him at 4 p.m. in the ICC common room. So you are all invited to go and ask the questions you didn't dare to ask now. And if there is no other question, we close it here. And we thank Carlos again.
Okay, thank you.